this is recording now. If you're joining now, hello, welcome. This is our paper discussion from the BSI subspace. This is part of the Brain Space Initiative set of activities and events. The goal is to engage with the community and learn about cool new stuff. Today we're going to be discussing a paper on graph signal processing, and our presenters are going to be myself, Rogers, Gaia, Derek, and Shanna. Sorry, I'm going to get that wrong. And we might have another person joining us well soon. So to get started, I'm going to share my screen. Let's see. Present. So we can see some of the slides that have been put together very nicely. Thank you for everyone who contributed there. And then sharing the screen. Good. So I think we can you see my screen? Not the right one, this one. Yeah. So I guess this is appropriate. This is the paper we're talking about. It's graph signal processing, an overview, challenges, and applications from Dr. Ortega. This is an invited paper at the IEEE, the proceedings of the IEEE from 2018. And yeah, we'll just give you a quick overview of how things are organized. This is a very informal, open discussion forum. If you want to chip in or ask questions, I think at any time is fine. We have assigned some roles to different participants. Today we're going to have these 4 roles represented. I'll be the scientific peer reviewer. Remind me, who's doing the archaeologist? I think we have 2 people doing the archaeologist.
I'm one of the archaeologists.
Good, Derek. And we also are going to have the academic researcher, and that's going to be Gaia and Guillermo. Going to be presenting that role. And we also have a private investigator presented by Shanna. And the idea with these roles is that each one of us looked at the paper with a different perspective and is bringing some new interesting summary of that research we did on the paper from that particular angle. So without further ado, I'll start with the first one. Sorry, not me. This is going to be Shanna. Shanna, you have the floor if you would like to get started.
Alrighty, awesome. Thank you. Hello, everybody. So again, my name's Shanna Hutcherson. I chose to play the role of private investigator for the first author, Dr. Antonio Ortega. So first, for some of his background, he had completed his undergraduate and master's in telecommunications at the Polytechnic University of Madrid, Spain, and his PhD in electrical engineering at Columbia University in New York. From there, he went to the University of Southern California, where he has stayed as a professor and researcher for the past 27 years in the electrical and computer engineering department, and served as associate chair. He is a fellow of the IEEE and European Association for Signal Processing, and is a member of the Association for Computing Machinery, and is editor-in-chief of the IEEE Transactions of Signal and Information Processing over Networks. So certainly highly regarded as knowledgeable in this field. And also Dr. Ortega has been working on a book for graph signal processing that should be available before the end of the year. We could go to the next slide. Okay. Okay, this is something that I thought would just be fun to add, really getting into my private investigator role here, is how Dr. Ortega is perceived as a teacher. And it seems he gives difficult courses with really heavy theory-based lectures, as you could probably imagine if you've read his paper, but he's been described as very helpful and caring to his students. And it was nice because I could personally see this consideration in his responses to an email I had sent him with a couple questions in preparation for this discussion. We could go to the next slide. So, one question being what led your interest in graph signal processing and motivated you to begin your research in it? And so, Dr. Ortega got started in the late 2000s before graph signal processing was really even used as a term. Although at that time there had been a few examples of graph wavelets already published at that time. And he actually came to the topic through his own work on sensor networks. And then, along with his students, he was working on algorithms for distributed wavelength transforms, which essentially allow sensors to exchange the data that they measure and perform like an in network transformation. And so they started by considering distributed wavelengths along paths or path graphs. And one of his students then found a way to extend this idea to routing trees or tree graphs. And then with another student, they had discovered ways to do this for arbitrary graphs, so not just trees and paths. And then soon they found themselves exploring applications then that had nothing to do with sensor networks, such as those that you might have read about in the applications part of the paper. And that brings me to my next question, because in the context of neuroscience research, which I think most of us are probably here for, we can use graph signal processing to infer a brain structure function relationship. And so I had also asked what he thought we should be careful about in collecting, processing, or inferring the data when using graph signal processing. And I really liked his response. And so I just put the whole thing here so I could read it out loud. So it reads, a primary challenge is that in this setting, one has to learn the graph first, and without a suitable graph, the results may not be meaningful. But we have no way of verifying that the graph we found is the right one, and in fact, in this scenario, a graph may be a good model, but it may only reflect at a course level what is really happening in the brain. I would say the key challenge then is to find ways to verify the relevance of the graph models beyond their ability to provide a concise model for the observed data. And I thought this was a really nice way of putting in context kind of one major challenge or question that neuroscientists have, which is, are these measures or techniques for analysis that we're developing, do they provide an accurate or meaningful representation of the brain? Something else that he had mentioned also that I will add is that he's also doing preliminary work in applying graph signal processing to EEG as well. Yeah, so that's all that I prepared.
That's pretty awesome. Thank you so much. Yeah. So, are there any questions or observations from the group so far? I find the background particularly uh, well done, and I appreciate the effort, especially the actual interviewing with him. I mean, through email, I think, but still, that was very nice. Thank you. And I think it it's a good introduction to the topic. Give some background of how he got started in it, and that he really is very well versed in the subject. Thanks. Anyone else? Okay, so we'll get started with the next one. This is my part. Uh, So
Can I
here,
say one thing? Sorry to interrupt. I jumped a bit late. I really like what everything you said, and also particularly the last part where the author emphasized, the importance of first learning the graph. Like this is an issue I was never aware of. So, it's very interesting. Thank you.
yeah, that's definitely one of the challenges. And I think this is a recurring issue with a lot of brain imaging research, that there is so much that we don't know about the brain. And I don't think we have so far found the one tool, and there's probably not one tool that is the best tool or the most appropriate tool to analyze the brain or particular types of data. Uh, and so it's a recurring issue that people sometimes don't understand that a lot of the research in brain imaging in general is exploratory, and we are trying to learn at the same time that we develop the methods, uh, and and so it's I think exploratory is the best way to define it. You take some data, apply some models to test some ideas, learn something, improve your models, test it again, and the process goes on. Sometimes you have a hypothesis, sometimes you don't, uh, and it's kind of like the nature of the problem that we have at hand. If we knew everything that's going on, it would be a lot easier to find and the right tools and narrow them down very quickly, compare them, and so on. So I think he brings a very important point that we have to verify the relevance of these particular models beyond just feeding the data. Uh, so I'll move on.
Can I just say something? But I don't know
Yes.
what you will think about it. Like, uh, from my point of view, the type of graph really also depends on the on what your what your problem is. Like, I think that for certain application there's not one unique graph, but you can but um, but you can find the best graph that kind of fits what you are um, um, uh, what you're working with. For example, if you want to um, if you want to use your graph structure in order to um, um, uh, to classify some data, you might let's assume that you are working with a particular rule for the for this classification, like uh, the items from one class are um, are smoother when projected on the graph than the items from the upper class. In that particular case, you are not very interested in the interpretability of your model, but just on the final application. And there are some techniques that allow you to obtain graphs that are just smooth for one class, but not smooth for the other one.
Yeah, I mean, you're basically describing a particular application that's for certain applications.
To
It
kind of
might.
like, oh, sorry, go ahead.
Oh, no, it's all right. It's all right. I was just completing my thought. I think that the application is also an important factor in choosing the type of graph. Uh, or yeah, I'll just mention that the particular model can also be driven by the application, not necessarily just the type of data.
Yeah, I was just gonna say, I think she kind of highlights something you could provide as a counter argument to the same thing is, does a technique have to be completely accurate representation of the brain if to have clinical utility in a sense? Like if a measure or technique seems to provide valuable information regarding a behavior or a symptom in a broad sense and it's improving patient outcomes, then maybe it's okay that it's not a completely accurate model of the brain as far as we can understand if it has some clinical utility.
Exactly.
Yeah, I agree with that. It's very much in line with what I think Dr. Ortega meant uh, with testing it beyond the fitting of the data. Uh, so, absolutely, I'm on the same page as well. Yes, yes. Okay, so we have some comments on chat that people are agreeing with our comments here. It's nice. If anyone wants to jump in, you're welcome to. This is supposed to be dynamic, so don't feel like you're interrupting. Okay, so I'll move on to a more scientific peer review part of this discussion. What I put together here is kind of a summary of how this method of graph signal processing works, and this is, I think, one of the strengths of this paper, in that it almost like it pretty much puts graph signal processing side by side comparison with digital signal processing. And I think this is very valuable for getting intuition about how the method works. I had some ideas before, and I think they got more clear after this particular set of comparisons. So the idea with graph signal processing centers around finding an analog to this delay operator, which is called a shift, and extending it to the graph case. And he starts by presenting it in the case of signal processing of temporal signals, one-dimensional temporal signals, and using this particular z inverse as the delay, as the indicator of the delay operator. He first presents this notion of representing signals as polynomials of this particular shift operator. And he also presents the traditional Fourier transform representation of discrete signals through these two forms, taking the signal and applying this operation on each sample to obtain the Fourier coefficients, and then the inverse Fourier transform applying this other operation to on each one of the coefficients to recover the signal from the Fourier domain. So this is the traditional DSP approach, and the shift operator can also be seen as a filter, a delay filter. And in particular, as any other filter, you would apply it to data by just multiplying the shift at each time point with the input data, and you will get the output. And in this particular example, he is assuming that signals are periodic. So in the case of shift, the output goes back into the input once it trails off the length of the operator. The shift operator is moving, shifting all points by one time point. But the length of the signal is not changing. And the assumption is that the sample that goes out of bounds enter, in this case, n minus 1, it goes out of bounds and enters back as the first sample. So
Uh, I have a question here. I
mhm.
thought this is what got me because they say that it is any filter edge, right? But it's not any filter. It's only
I
LTI that
think
can be represented using it, right?
it's only what?
LTI filters, linear time invariant. So essentially, time varying and nonlinear filters can't be done like this, I think.
Yes, he did mention at some point that this is linear,
Yeah,
restricted to
yeah.
linear.
But here he forgot because I remember somewhere he said that, yeah, we are gonna talk about LTI.
Hmm. Yeah, I remember seeing him indicating it somewhere in the paper, maybe in the introduction or the first section, where he was just saying, on the for the scope of this paper, we're going to be focusing on linear models.
Yeah, I just wanted, so LTV filters can't be represented by shifts, right? Only shifts and
I mean, that wasn't described in the paper, so I think I agree with you.
okay.
Yeah. Uh, all right. So then the idea is that in this case of linear filters or linear systems, you can represent this any filter is the proposition here, using combinations of these shift operators in series or in parallel combinations, uh, and effectively construct any kind of filter. I also think that he's restricting himself to causal filters, FIR filters. So that's another point to take into account. And then he presents for the traditional DSP case a property that if you uh, apply shift to a signal and then filter, or filter and then apply shift after filtering, the outcome is the same. And that's an important property that he's gonna leverage or try to replicate in graph signal processing. So then moving on to graph signal processing, the first thing that I liked here is building an analogy from a graph perspective of the DSP case that we just looked at. So how would you go about applying filtering in this signal if you were to represent it as a graph? And here the graph is in time. So each sample, in this case, this is a cycle graph where one time point points to the next time point and so on, and the last one points to the beginning. That's the definition of the shift operator. And this can be represented in graph form using a cycle graph like this, where rows and columns represent where you're coming from, and rows represent where you're going to. So sample 0 goes to sample 2. This is what it's saying. So when you apply a shift, the value at this node moves to this node, and so on and so forth. And you can obtain that by a matrix vector multiplication of the signal by this particular matrix that represents the graph. And then the notion is that with any filter, you could represent any filter by a matrix vector multiplication, not just these types of filter. And he also introduced these quantities, which are the adjacency matrix, which is like this matrix, but with not restricted to zeros and ones, and you can have multiple connections between nodes. and also the Laplacian matrix, which is a particular type of matrix based on combination of the degree matrix and adjacency matrix, and also a normalized, a symmetric normalized version of the Laplacian matrix defined like this. This is just to say these are the three types of matrices that are graphs that are graph matrices that are considered here: the adjacency matrix and two versions of the Laplacian matrix that are derived basically from the adjacency matrix. And those are the matrices that are going to be considered in further. And then I think this is my last slide. The idea to extend the notions from digital signal processing to graph signal processing is one, we want this property to remain, which means whether you shift the signal before or after, it doesn't change the outcome. And in this case, the notion is if you permute the columns and rows of the graph, the result doesn't change. That's the intuition in the graph signal processing case. And then the notion of Fourier transforms extends to the graph case by thinking of this decomposition of the adjacency matrix into the Fourier transform. Basically, this is like a singular value decomposition of the adjacency matrix. And then if you wanted to represent a signal using graph Fourier analysis decomposition, the idea would be to just apply the Fourier transform to your signal to obtain the coefficients. And this is now just a matrix multiplication where this particular basis, the Fourier basis, is derived from the graph itself, from the adjacency grid. Either the adjacency matrix or also could be derived from the SVD of the Laplacian matrix. The main difference between the adjacency and the Laplacian matrix is that in the Laplacian matrix you would sort your components based on lowest to largest variance instead of largest to lowest, which is the case for adjacency matrix. And then this is how you would go about filtering a signal using graph signal processing. Basically apply the filter to your signal by matrix multiplication, and then you can show that this basically boils down to you can write this as a Fourier transform of the signal, which in turn you can write as a graph filtering of the transformed signal, and then recovered V here is the same as the same Fourier basis. Then you can recover the signal back. Basically what this is saying is you can imagine that this is filtering. Filtering is like moving your signal to the frequency space. And here it's a frequency defined by graphs. Filtering in that space by matrix multiplication, and then transforming it back to the original domain of the data. So then this is the gist of what graph signal processing is and how it's defined. And I found very, very useful the analogy of the the delay, the shift operator, and describing it as a graph. What I thought was missing here was that in the transition to the graph signal processing presentation, I didn't see a connection with the same example of signals over time. That there was just an explanation that there was no discussion of signals over time like this when you actually got to general graph signal processing on arbitrary graphs. And in particular, I would have liked to see, to have seen something like this kind of analogy on multiple signals that are also moving over time. So I think, in my mind, I think I could see like something like having one of these cyclic matrices for each pair of signals, so that you're representing the structure over time and the relationship between signals. And I'm thinking like EEG data would be like that. You have multiple nodes recorded at the same time, and they're all temporal signals. So I think you could have a structure like this, a graph representation like this for time, for the dimension of time, and then the association between nodes represented as a full adjacency matrix, or something of the like. I would have liked to see a description more specific to that. And then, if I may, I would just, to wrap up, give an example here of this discussion, illustration, I'm sorry, of the kinds, just to give a notion of what frequencies are in this graph domain. So this is the singular value decomposition of the adjacency matrix here at the top, and it's ordered by from lowest to highest frequency, and this is largest eigenvalue. So in the largest eigenvalue of the adjacency matrix, you get the lowest frequency, and this is comes out as a smooth graph. Is the idea is that these colors are smooth and not varying very much, the values here. That's the notion of low frequency. It's more general than frequency is more general than the traditional case of temporal signals. And then here, as you move on, you get higher and higher degree of variation between the values in the nodes, and that's characteristic of higher frequency. And the same notion goes here for the SPD decomposition of the Laplacian matrix, except that the lowest eigenvalue is the one that represents lowest frequencies. And you can get some effects on the higher frequencies for the Laplacian matrix, where only a subset of nodes is actually non-zero, which I think the relevance of this depends on the specific application. And in general, the paper is, I think, is well organized, does a good job of presenting the history of related areas, and also does a good job of the current issues, the current difficulties with these methods and the direction that the research is going. So are there any questions up until this point? I think this is the end of my part here. I think, as a reviewer for this paper, I might recommend minor changes here and there, specifically with this, expanding a little bit further the notion of vector signals evolving over time. But overall, I think I really like the way it's presented and the way it's organized. So I would recommend only minor changes. Are there any comments?
So what do you mean want to add time to it. Because I thought that essentially graph signal processing is essentially generalization of time instead of signals being
Well, it depends on your definition of nodes, right? So if nodes are time points, then yes, it's exactly as he showed. The analogy is this one. But when you extend this matrix to be other things, say if you just added more ones here, it means there are more connections from different time points into the future, right? Or back into, because this is cyclic. Well, doesn't have to be.
but
Could be a upper
that won't
triagonal.
be time series again. I think time series only can have this specific AC, right? The digital signal processing time series is literally only
True.
this.
Yes, but you still can think of multiple signals, right? Like an EEG recording. And if you ignore the, momentarily, you ignore the temporal structure and just think of a single time point, those time points may be connected through a graph. That's what I'm trying to say. You can think of the distance, physical distance between electrodes could be what defines the adjacency matrix between nodes. So you could define a node that way.
So I think this definition of a graph is separate from the digital signal processing case in the sense that like one is in the time mode, like it continues, operates on the time axis, and the other operates on the axis for sensors. So it definitely makes much more sense to apply the graphs on that axis. Like for example, for EEG, as you said, applying a graph or modeling it as a graph makes much more sense. But on the other hand, if it's in the time axis, this makes more sense. So there are two separate graphs of interest here.
Yeah. So what I was trying to get to is that I think we could combine the two into one graph, one super graph that describes
So
the temporal graph together with the between node.
so in that case, you are talking about multi-layer or multiplex graphs, since the modes. So multiplex graph means that at each time point you have the same graph, but the graph evolves. So that graph evolves over time, and it is called a multiplex graph. And every node is repeated at each time point. If it's a multi-layer graph, every node doesn't have to be. But anyway, like there are definitions of those types of graphs. But I understand the reason why it's not mentioned here because it's kind of a bit of a specialty in the graph theory part. So I would say like multiplex graphs in that case is creating a much more interesting definitions. It's because it's a bit vague. There are not like straightforward answers that it relates to DSP.
Yeah. Okay. So I did not read about those kinds of graphs, so I can't really comment. But I'm not sure that the idea that I had in mind, at least in my head, I don't think it was that the graph was changing over time. I still imagined that it was static, only that it
So
was also capturing this temporal
yeah,
graph.
so is it like the nodes are the same? The nodes are the same, but the adjacency values or the neighboring values might change over time.
Um,
So let's say that
how could I describe
there
it?
is this error-related potential in the EEG, and that evolves over time. Different nodes, you have different connections. From resting state to error, like that response state, the brain network kind of differs. So in that case, it's not that the nodes are changing, but the adjacency values of the nodes are changing. Is this something like that? Am I getting this correctly?
Um, okay, so I think what I meant is, imagine that you have a single time point and you have 20 nodes for uh, 20 for the 20 electrodes. But you're taking only a single time point, and then you have an adjacency matrix between them. Now you can write that adjacency matrix, but I think you can also think of each element, like replacing each element of the adjacency matrix with this matrix here, with this cyclic matrix. So it basically expands the full graph to include, so that each node represents not only the electrode, but the specific time point in the window that you're filtering as well. So
Okay, I understand.
you have that multiplication of number of nodes as a function of the window length.
It
Oh,
would
So
be
that's
like
that's how I was imagining.
it would be like a transition matrix between time step one, for example, to the next time step. So you have the just in the same example as the figure 2 with the state 0, state 1, and state 3, but you kind of extrapolate or compute an approximate transformation in a numerical way through this matrix that would let us going through the state 1, 2, 3 in a very computational way. So I believe that it would be like a spatial pattern that would be captured by the adjacency matrix, but at the same time, there will be like a temporal transformation matrix that is getting advantage of the temporal pattern that is being modeled
Mm-hmm.
as a graph. So it's a multiple approach, I believe. I'm not sure if I captured the idea.
Yeah. I think that's a closer description. I like if I could scribble something, I would uh, try, but I won't try on this format. Uh, but I think those two ideas are the multigraphs and what you this multi approach that you described. I think they're related to what I'm thinking. I'm not sure it's exactly the same thing, but in the interest of time, I want to make sure that everybody gets a chance to speak. I will move on to the next part, which is uh, Derek is going to be talking about. Uh, he took the was it archaeologist role.
All right, so given the scope of this paper, there was a lot I felt like we could have done in going backward to pick a previous paper that really informed what they were saying here. But I went with this 2013 review by Mora, and who was also a co-author on this paper. And I'm happy to be corrected by those of you who are more in the know than I am. It seemed to me my take home from that 2013 article was maybe that was one of the early papers to really introduce really everything that Rogers just talked through in linking a digital signal processing framework to what we might want to do with graphs. And so my sense was this 2013 review was really asking the question, can we adapt these techniques to analyze time series that exist on graphs, so preceding or predating the current paper by about 5 years. And then 5 years later, it's about time to really reevaluate where we're at and how this has been used. So this was my attempt at kind of summarizing what each of these pieces, the shift, the filter, and the Fourier transform are in my plain language. So the idea, you can, again, I invite corrections here. Graph shift, we're replacing the graph signal with a combination of neighboring signals. The graph filter, we're decomposing the graph into its constituent parts. It really spoke to me. There was comparing it to a linear regression with constant coefficients. And then in taking that filter and applying the Fourier transform, using that and applying it to the signals, we're able to characterize whether those stables are stable or unstable, or whether the signals are, in our terms, coupled or decoupled from that underlying graph structure. So I felt like this was an important and well-cited paper that led to the current indicted review. You can advance slide.
Oh, sorry. Yes.
And again, a lot to choose from. I went close to home on this one. They had a few sections definitely of interest. I know somebody in the audience mentioned they were doing some work with motion capture, different sensor-based networks that I'd love to hear what's going on in that world. In my world, as Shanna mentioned, we're interested in using graph signal processing to relate brain structure and brain function. And so one of the papers that cited the current one was one that was recently published in 2020, and this was an analysis of 55 former athletes who had a history of multiple concussions, and the authors proposed then that they might be at risk for developing what's known as CTE. That definition is quite ambiguous, but they might be at risk for unhealthy brain aging, we'll say. And they compared those former athletes to healthy adults. Age-matched healthy adults, not former athletes, didn't have a history of concussion. The graph, in their case, was a structural connectome produced by diffusion-weighted imaging. They mapped it to a standard atlas that considers the brain to be broken into 66 areas. And so the graph was a 66 by 66 weighted symmetric graph. And the graph signal came from resting state functional imaging, which included 150 TRs. So this is a bold time series sampled over about 5 minutes. And then they did something interesting that I'm sure many of you experts on the call would want to know more about, in that they took this windowing approach to compute dynamic functional connectivity on the GFT filtered bold signal. They actually claim in the conclusion or in the discussion that they believe this to be one of the first uses of this graph filtering technique to compute dynamic functional connectivity. And in doing so, and performing some different permutation tests, both parametric and non-parametric tests, to, at the end of the day, approximate whether there were differences in dwell times between these states characterizing the former athletes and the healthy adults. And they come to the conclusion that there is. And if, I would encourage anybody who's interested in this to maybe go look at their appendices. It's interesting. They present the same data without the graph signal filter, and it looks almost identical. So one of my questions coming out of this article, the current article that's on the slide, back to the article we were reading, was really wondering how necessary this was to the points that were raised at the outset of the conversation. What do we gain from doing graph signal processing in this approach?
Very interesting. So the point here is that the result seems to be unchanged whether you filter or you don't filter. Is that what you're trying to say?
Yeah, correct. Yeah, thank you. Exactly. There was to say that differently in relation to their hypotheses or their questions. There was a difference between healthy adults and former athletes in both cases. Both of the states that were derived looked very similar anatomically, and the effect sizes were very similar.
So this paper, did they? Sorry, go ahead. This paper, can you hear me?
Yes, you can.
This paper, did they? I'm looking at it. Did they filter using graph filtering, then calculate, for example, I don't know, window DFC, or they used graph filtering to calculate DFC?
It sounds to me like it was two steps. Sorry, Derek, you can confirm.
No, I think algorithm one, top of page 289. I think they're explaining this, and I think I got your question. So they're filtering the bold signal and then computing, then doing this windowing to get dynamic connectivity.
So it is, yeah. Okay, so it is,
which is interesting given what we were just talking about. I think, why not? It sounds like they could have taken a graph signal approach to decomposing the filtered time series as well, which I didn't consider prior to this conversation.
Yeah, I'm inclined to think that, applying the approach on the time domain as well would have been very interesting. Yeah, I think it's worth looking into this particular application and take into consideration the points we discussed before, like where what is did they use the appropriate graph? Was that the appropriate choice for this problem? Have they considered alternatives, and what do we gain from this type of technique? I think it's, you know, in of itself, it's not sufficient to as a demerit for the approach, but it raises a question. Uh, so I think it's worth pursuing that question and trying to understand further. Do
Certainly
we have
relating
more
these
slides?
patterns to behavior would have been helpful to our point.
I think we have a couple more people who were going to present something. Let me see, who were those? So we had Shanna, Derek, Guillermo. I think Guillermo or Gaia, one of you two can add your points in terms of academic, the academic researcher goal role.
I don't have any slides, so if you do,
Sure.
Guillermo, you can start. Otherwise, I can.
I don't either, so
Okay.
That's
if
okay.
you want,
So
you can go.
I'll just keep on screen here. Actually, I can stop sharing so we can see our faces on the recording. There.
Okay, so what I like, I had two main ideas. The first was based on a spectrum decomposition based on graph allows you to have a view of um, of uh, um, of uh, of of whether different areas of the brain are collaborating or not during a given task. Because low frequency components can be associated with similar values of the signals over the graph, while high frequency components could be associated to at regions that are not really collaborating with each other. So what I was thinking is that it would be interesting to see uh, uh, what is a graph model for this functional organization when different subjects are executing the same task. So to see if they all have similar patterns of segregation, I think it's the correct term in your science, and if in the contrary they are like working together, not working together, I don't know if it's clear.
Mm-hmm. Yeah.
What do you think about it?
I wonder if we, you know, looking at consistency, sort of this, consistency across subjects would definitely be very interesting. So if it's task-based fMRI, it would definitely be. I would expect to see an effect there, a strong effect, because there is a an external driver of the signals. It would still be interesting to see if the segregation of nodes would look similar across subjects, because this, although the graph is the same. Oh no, the graph would be the same though, right? The graph is not defined by the data.
You can like I was thinking of, yes, fixing the same graph, like based on structure in this case, and then see um, uh, based on the on the same graph, which is the spectrum condition under different tasks for different patients. And what I think is interesting is to also compare uh, these 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 structures for patients that have different different diseases, for example, and to try to and to try to infer a pattern behind it.
Yeah. So one thing that I'm new to the area, so I may not be. I think many of us here are, but I feel like we could, in this particular application, we could, because the graph is the same, we could even do sort of a, I don't want to say a harmonic analysis, but like a frequency analysis where we basically apply this. What I'm trying to say is try to recover the representation of the time series for a particular frequency. I don't know if it makes sense.
You mean first computing the Fourier transform in time domain for each electrode kind of?
No. What I was thinking is looking. You can represent signals by using graph signal processing, right? So using one of the bases of the adjacency matrix, for example, and then you can, because the graph is fixed, there's only one decomposition, and if you look at at, if this were, for example, the Laplacian, it would be almost like looking at graph cuts, like how the different nodes cluster together, depending on the particular eigenvector that you're looking at. So in that sense, the graph is not changing over subjects, but something is changing, and what I think is changing is the coefficient, the Fourier coefficient for that particular graph, right, on each subject, or to some extent, I think you could capture how strong that coefficient is in a subject. And if you could get that information, then you could look over subjects how these different clusterings are represented or occurring to the extent to which they are occurring in each subject. Yeah. So does that make sense? Maybe
Are you suggesting finding bases using group and then finding
Yeah,
the
exactly. Finding.
okay.
I mean, the bases are defined by the graph, and they are the same for all subjects.
Yeah, and then finding the essentially finding the Fourier
Yeah.
bases using the group, and then finding the Fourier coefficients based on the
Exactly.
subject.
Yeah,
So
I
in
wanted
that
to.
way, so sorry. So in that way, you are looking at the spectrum, right? So at the at the projection of the signals on the graph.
Exactly. Yeah.
Yeah.
And is that the sense that you were describing, that you could compare subjects?
Yes.
Awesome. Yeah, I think that makes sense. So we're running over a little bit. Guillermo, do you wanna share your idea for a research project?
Yeah, well, actually, I started with a different idea. and the one
Mm-hmm.
I'm going to present now. After the discussion we had just like a few minutes ago, it just came to my mind that a graphical model that allows to interpret temporal structure in the neural networks approach is LSTM. And after we were discussing, I'm curious about the relationship that the LSTM approach has with some kind of graph temporal approach as you were discussing. I mean, for example, when we are trying to use LSTM to model sequences, we have we have to define how many units we are going to have in the LSTM network. And according to that, it would be like we have, let's say, 10 units. And in the graph temporal approach, you would have like 10 units, but these are 10 units of different nodes that are related between each other in the more matrices transformation sense. It wouldn't be like in the LSTM a more gradient oriented approach. So I'm curious if both approaches can have an equivalent if the relationships make sense, because it kind of makes sense graphically seeing both of them, that we have the units, they have the relationships, they can have long or short-term dependencies, but at the same time, the way we can extrapolate transformations is really different. From one side, it would be the learning computational gradients and all of the story behind the LSTM training, and the other one would be more signal processing approach in which we are not dealing with a lot of data with training, but instead we have to kind of design the whole process. So that's something that I was thinking about just now. But and very briefly, the idea that I was preparing was more into the how can we explain graphs in a more human way. I know that there are this term, which is explainable artificial intelligence, and without making apart the signal processing topic by itself, there is a very small section in the paper that they dedicated to the graph learning. And well, if we can explain graph structures from the standard machine learning process that is applied to the graph training by itself, the graph learning, then I believe that we could have more insights about the structure of the brain computational processes, the inner brain computational processes. And for example, with EEG, there might not be a lot of insights about the internal functional connectivity, but with some other things, we may have more insights and more meaningful insights that can be related to our own expertise. Because when we are, for example, trying to classify EEG signals, um, in the end, what we want is that the output target, output class of the whole classifier matches with what with with our label. So if it's not trained in the very efficient way, it's not going to match. But at the same time, what is the reason of this training or misbehavior of the classifier? And perhaps explainability from the graph signal processing approach can provide some insights. Well, those are my ideas. Um, yeah,
Mm-hmm. Yeah, that's very interesting. I mean, mm,
Can you explain more on the LSTM idea? I'm curious. I, I I'm not the expert on the LSTMs. I'm not the expert on graph signal processing as well. But how do they relate? Like how do you find the relation in between?
yeah. Well, the LSTM can be think of a unit that has inside some gates, right? And it has an input, an output, and kind of memory inside that is holding the previous state. And according to the relationship with other units, you can also have like a relationship to other units that are far apart. So you can extract a pattern which is in a long term. That's why the reason it says long short-term memory. And I was thinking on the very same figure that Rogers was talking about, in which we have a very large arrow between the state 0 and, for example, state n, and that would be like a long relationship between one unit and the other one. So there is an internal state on the LSTM, but at the same time, there's an internal state for the node that we are looking for. So it kind of makes sense to me to think of the unit after unit, and between all of them, relationships, short-term relationships, and also the long-term relationship as in the LSTM. I'm not sure if that clarifies more my idea.
Yeah, I can see that. So it's
Yeah,
like
so
the FIR filter is kind of similar to an LSTM, yes. Only that the LSTM has a far more longer relationships, and there's also the nonlinearity part. And yeah,
yeah, I think the challenge with LSTMs would be to describe it in terms of a graph. From the perspective that you're proposing, you would need to know from your inner state what are the previous time points that are contributing to it the most, and then just because the way it's trained, it's very well set in stone. It's like it's not very clear, I think, how you would get that get that information to try and build the graph. Uh, but I wonder if there is a way that we could uh, bring the notion of graphs into maybe the features that go into the LSTM. I, yeah, without just hand waving, I can't be very specific, but I think there might be a way to
Well, you
to
can do the temporal graph, right? AC. The time series that goes has the temporal graph in it. So
right. But then in that part, if you use that temporal graph in particular, we are basically doing basic digital signal
yeah,
processing. So
yeah,
we're just using the Fourier transform.
yeah.
Like, to make it more interesting, you would need a more elaborate graph structure. So I'm not sure. I feel like that there might be a connection in there because it definitely makes sense. You have nodes and you have time, and in both models, and in yeah, it feels very interesting. But I can't put my finger exactly on where the connection would be.
I didn't really get your question.
So the idea is how could we combine, or where is the connection between graph signal processing and a model, say like LSTMs, where you both models are processing could process data over time, and you could have in both models multiple nodes at each time point. And I think it depends. It's not clear how you could build a graph, either build a notion of a graph inside an LSTM, or bring notions of LSTM like memory and so on into a graph signal processing technique to merge the two. It seems that there is a connection, but it doesn't seem very
so
obvious.
so to my like to a bit of an insight maybe. So there is this exactly Armin Raji pointed out. So there is this autoregressive model, and you learn the weights of the graph basically in LSTM. So the long-term memory, short-term memory, the separations of it, the weights of it, basically the adjacency is kind of structured within the weights of LSTM. So how do you weight each node? You are kind of learning the graph along the way, but the graph structure is set in stone with LSTM. So you kind of know how to
I
go
see.
back. The graph nodes actually, well, they always have to be set in stone anyway. That's my understanding. But when there are more than one-time signals, like in EEG, for example, you have more electrons, then the relationship in between them also makes interesting. That might also be interesting to think of in terms of getting an output from one node in LSTM. So there are other nodes in not time, but in space that might be related to that specific node.
Interesting. Okay. Yeah, I think that makes sense. You know, learning the graph uh, a- as the way to make the connection. That's pretty nice. Um, so I think we went over everyone who had signed up to present. Uh, this is a little overtime, like I said before, so I don't want to hold you. But if there are any more questions, I think some of us may be available for a couple more questions. Uh, it could be just comments on the paper itself. Okay, I'm looking here at the chat, and there might be something. So there is a question to Derek. If you could put the name on the paper on chat. Armin is asking.
Which paper?
The last one that was looking at the study on functional connectivity they were using. The study on TBI concussion, please, if you don't mind. Thank you. I appreciate it.
Yeah. Okay. So I'm looking at the chat right now. I don't know if this is showing the recording, so I will see here if I where does it start? So Ashkan who made the comment, but it's a while back now. He pointed to another paper. Yes. Well, there's you can see the link on the chat for this other paper. What is this? If I click, does it go? Are you seeing my screen? Oh no, I'm not sharing. Let me share them just so there's a record. So this is another paper I think Ashkan was sharing. Am I right, Ashkan?
Yeah, I think Derek shared the same thing. Yeah, yeah. I think this was the whole issue was about graph signal bar. Not sure, but and this is the same not issue.
Oh, it's in the same issue
I
as
think so.
the paper
But
we
it
just
is
read.
with Dimitri Dimambila and Daniel Bassett. So it is a little more graph oriented than signal.
Oh, I see. So this is the paper that Derek was talking
Yeah,
about.
I
No,
think
I
so.
see the connection. Thank you. Yeah, okay, so you already discussed that. Sorry, I was catching up late. Good, awesome. Then I think that covers everything that was on chat. I will let's do this. I will save the chat for the record. Let me stop sharing. Then it's easier to do that. And then we can, if there's maybe one more question that or a comment that anyone wants to make. Let me put an open question here. Does it excite you enough to look further and see if there is a way to apply this on your research? This particular application, this particular method. I'm getting some yeses. Good. It's great reaction. How about this? Would you guys be interested in suggesting another methods paper a future uh, for a future meeting? Just so that it's not like unilateral decision. I have some already on the queue, but if you guys have any suggestions of methods you would like to discuss more and so on, I would suggest then to put those suggestions on Slack. We can build a list, and maybe we'll have more of these more often. Have these events more often. How do you like that idea? Did you like the format, by the way? Yeah, I especially like the way that we come at the same method from different angles. Great. Cool. Okay, so I will stop the presentation here then. If there are no other comments, said I was gonna save the chat. Okay, I'll do that after we stop here. I wanted to thank everyone for coming by. I will keep a record of the chat, and I also have a record of this meeting, the video and the presentation, and I'll make all that information available on Slack. And if you guys want to continue the discussion on Slack later on, that would be awesome. I think everyone here will be open to expanding their points and what they meant, if anything wasn't clear. And I wanted to thank everyone for coming by, and look forward to seeing you on to discuss one other paper later on. Thank you so much, guys, for stopping by.
Thank you. It was nice to meet everyone.
Thank you.
Thank you.
Yeah. Thank you, guys.
Thank you.
Thank you. Bye.
Have a good day.
Bye.
Bye-bye.
You too.
Bye. Good night.